Picture the universe stretching out around you, a vast and ever-expanding canvas of darkness punctuated by billions of glittering stars and galaxies. It's a breathtaking sight, one that's not just beautiful but filled with motion, a cosmic dance that's been unfolding for nearly 14 billion years. But here's something that might catch you off guard. What if I told you that most of what's driving that expansion isn't just invisible to our eyes? It's something we fundamentally don't understand. Imagine this: 68% of our entire universe is made up of a mysterious, elusive force known as dark energy. And this isn't just some abstract idea tucked away in scientific papers. It's actively, right now, pulling the fabric of our cosmos apart faster and faster, shaping the ultimate fate of everything we see and everything we are. This isn't science fiction. It's one of the most profound and puzzling realities modern astrophysics has ever uncovered. Think about that for a moment. The majority of our universe is composed of something we can't see, can't touch, and can't even fully describe with our current laws of physics. It defies intuition, challenges our understanding of reality, and leaves even the brightest scientific minds grappling with questions that stretch the limits of human knowledge. Why is the universe accelerating in its expansion rather than slowing down? What could possibly be fueling this cosmic speed-up? And perhaps most intriguing of all, what does it mean for us, living our lives on this tiny, fragile planet suspended in such an immense and mysterious cosmos? That's exactly what we're diving into today, a journey through 25 of the most captivating and confounding mysteries surrounding dark energy. We'll explore everything from its eerie discovery in the late 1990s to the mind-bending theories trying to explain its nature, and even what its existence might imply for the long-term future of the universe itself. This is more than a science lesson. It's an invitation to wonder, to question, and to stand in awe of just how much there still is to learn about the cosmos we call home. So settle in, open your mind, and get ready to explore the enigmas of dark energy, the invisible architect of our expanding universe. To truly appreciate the depth of this first mystery, we have to rewind the cosmic clock back to 1917. Albert Einstein had just published his theory of general relativity, a revolutionary framework that described gravity not as a force, but as the curvature of space and time itself by matter and energy. When he applied his magnificent equations to the entire universe, he encountered something unexpected. The universe his math described was dynamic. It was either expanding or contracting. But this flew in the face of the scientific consensus of the day, which held that the universe was static, eternal, and unchanging. To force his equations to match this prevailing belief, Einstein introduced a fudge factor, a term he called the cosmological constant, represented by the Greek letter lambda. This constant represented a kind of repulsive energy, a pressure inherent to the vacuum of space itself that would perfectly counterbalance the inward pull of gravity, holding the universe in a state of perfect, motionless equilibrium. He later famously called this addition his biggest blunder, after astronomer Edwin Hubble discovered the universe was indeed expanding, but the story doesn't end there. The plot thickened dramatically in 1998 when two independent teams of astronomers were observing distant supernova. They weren't looking for dark energy. They were trying to measure how much the universe's expansion was slowing down due to gravity's relentless tug. To their absolute astonishment, they found the opposite. The expansion wasn't slowing at all, it was accelerating. The universe was flying apart faster and faster as time went on. Something was overpowering gravity, and that something behaved exactly like Einstein's discarded cosmological constant. In a stunning twist of fate, his so-called blunder was resurrected as the simplest explanation for dark energy, a prophetic idea decades ahead of its time. This is where we arrive at the heart of the mystery, a problem so severe it's been called the worst theoretical prediction in the entire history of physics. According to our well-tested theories of quantum mechanics, the vacuum of space isn't empty at all. It's a seething, bubbling foam teeming with virtual particles that constantly pop in and out of existence. This quantum frenzy should endow every cubic centimeter of space with a certain energy density, a vacuum energy. We can actually calculate what this energy should be based on our understanding of quantum fields. When we do, the number we get is astronomically, unimaginably huge. Now, astronomers can also measure the actual strength of dark energy driving the cosmic acceleration. The two numbers, the theoretical prediction from quantum physics and the observational measurement from astronomy, should be the same thing if the cosmological constant is the answer. But they are not even close. The value predicted by quantum theory is larger than the observed value by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros. To try and grasp the scale of this error, it's not just like measuring the distance to the moon and being off by a millimeter. It's like measuring the entire observable universe and being off by the diameter of a single proton. The discrepancy is so vast, so complete, that it tells us with absolute certainty that something is profoundly wrong. Either our understanding of the quantum vacuum is deeply flawed, our interpretation of gravity through general relativity breaks down on cosmic scales, or we are missing a fundamental piece of physics that somehow cancels out almost all of this vacuum energy, leaving behind just the tiny, faint whisper we detect as dark energy. This isn't just a gap in our knowledge, it's a yawning chasm that lies at the very foundation of reality, challenging the core pillars of modern physics. This leads us directly into the second profound mystery, one that is perhaps even more philosophically troubling than the first. It's known as the coincidence problem, and it asks a deceptively simple question: why now? Of all the countless eras in the entire 14 billion-year history of the universe, why do we find ourselves living at the precise moment when the effects of dark energy and the effects of matter are not only both significant, but are almost exactly comparable in their influence on the cosmos? To understand how strange this is, we need to think about how the density of matter and dark energy have changed over cosmic time. In the early universe, just after the Big Bang, everything was incredibly dense and hot. Matter, both the normal atoms we're made of and the invisible dark matter that holds galaxies together, was packed tightly together. Its gravitational influence was overwhelming. For billions of years, this matter density dictated the fate of the cosmos, slowly slowing down the initial expansion. Meanwhile, if dark energy behaves like a cosmological constant, its energy density would have been spread evenly throughout the vacuum of space, remaining constant and unchanging since the very beginning. And that's the core of the problem. Because the universe has been expanding, the density of matter has been dropping dramatically as particles spread out into an ever-increasing volume. Think of it like a drop of ink in a growing glass of water. It becomes more and more diluted. Dark energy's density, however, stays the same. So for the vast majority of cosmic history, these two values were wildly different. In the first few billion years, matter density was astronomically higher than dark energy density. Gravity was firmly in control. In the far, far future, matter density will have diluted to almost nothing, while dark energy's constant density will completely dominate, leading to an empty, accelerated expansion. The period of time when these two densities are within a few orders of magnitude of each other, when they are even remotely comparable, is an incredibly brief window in the grand timeline of the universe. And we just happen to be here, alive and conscious, right in the middle of that special window. The odds of this occurring by pure random chance seem vanishingly small. It feels like tuning a radio and finding a clear, strong signal from one specific station, only to realize that if you had turned the dial a fraction of a millimeter earlier or later, you would hear nothing but static. This has led some scientists to propose that it might not be a coincidence at all, but rather a necessary condition for our existence. This idea is known as the anthropic principle. In its simplest form, it suggests that the fundamental constants and conditions of the universe must be compatible with the existence of observers who can measure them. We shouldn't be surprised to find ourselves in a universe that allows for life, because we couldn't possibly find ourselves in one that doesn't. In a universe where matter density dominated for too long, gravity would have potentially caused a catastrophic big crunch, collapsing everything back in on itself before stars or planets could form. In a universe where dark energy dominated too early, the rapid acceleration would have ripped proto-galaxies apart before they could ever coalesce, preventing the formation of stars, planets, and ultimately us. So, the argument goes, we can only exist in that narrow sliver of cosmic time where the balance is just right for complex life to evolve. This perspective is both powerful and, to some, profoundly unsatisfying. It can feel like giving up on a deeper explanation, essentially saying, things are this way because otherwise we wouldn't be here to see them. It challenges the very core of the scientific pursuit, which is to find fundamental, predictive reasons for why the universe is the way it is, not just a post hoc observation about our place in it. This mystery forces us to confront the nature of our reality itself. Is our universe a single, finely tuned miracle, a perfect and unlikely accident? Or is it just one among a vast multiverse of universes, each with different physical constants and laws? In that infinite landscape of possibilities, it's no surprise that we find ourselves in one of the rare universes where conditions are hospitable. The coincidence problem doesn't just question a number in a physics equation. It questions whether we are the product of chance or necessity, and whether the cosmos was in some way expecting us. But what if dark energy isn't a gentle, constant pressure, but something far more menacing? This brings us to our third mystery, a concept so unsettling it sounds like it's ripped from the pages of a cosmic horror story. It's called phantom energy, and the fate it predicts for our universe is perhaps the most violent end imaginable. To grasp this, we need to understand a specific characteristic of dark energy known as its equation of state. Scientists describe the nature of dark energy using a parameter labeled W, which is essentially the ratio between its pressure and its energy density. For Einstein's simple cosmological constant, this value is exactly -1. This gives us the constant, steady acceleration we've been discussing. But what if observations told us that W was not just -1, but something even more negative, like -1.1? That small numerical shift would completely change the nature of this mysterious force and the ultimate destiny of everything. This is phantom energy. Unlike a constant vacuum energy, phantom energy would have a truly bizarre property. Its energy density wouldn't stay constant as the universe expands. It wouldn't even just increase slowly. It would increase without any limit, growing exponentially stronger over time. This isn't just a universe expanding faster. This is a universe where the very engine of expansion is becoming infinitely powerful. The consequence of this runaway effect is a cataclysm known as the Big Rip. Let's walk through how this would unfold. First, the accelerating expansion would eventually overcome the gravitational glue holding the largest structures together. Clusters of galaxies bound by immense gravitational forces would be the first to be pulled apart. Billions of years later, as the phantom energy density continues to swell, individual galaxies themselves would be torn asunder. Stars would be flung out into the ever-emptying void, their solar systems scattered like dust in a hurricane. But the horror doesn't stop there. As the force continues to intensify, it would eventually overcome the electromagnetic forces holding individual stars and planets together. A planet like Earth would be ripped apart, its continents shattering. Then it would overcome the nuclear forces holding atoms together. Molecules, then atoms, and finally the very nuclei of atoms themselves would be torn to pieces. In a finite amount of time from now, every single bit of structure in the entire universe would be reduced to a sparse, expanding cloud of fundamental particles that can never again interact, a cold and absolute end to all things. The truly chilling part is that some observational data, when analyzed, doesn't completely rule this scenario out. Measurements of the cosmic microwave background, supernova, and baryon acoustic oscillations all try to pin down the exact value of W. The consensus value is very close to -1, consistent with a cosmological constant. But the error bars on these measurements, the range of uncertainty, sometimes dips slightly below -1. It's not a definitive detection by any means, but it's a persistent whisper in the data that this most terrifying of possibilities cannot yet be entirely dismissed. This leaves cosmologists in a deeply uncomfortable position, balancing the most likely explanation against the most dramatic one, all while knowing that the answer holds the key to whether our universe will fade away quietly or end in a single, blinding moment of catastrophic violence. Faced with the stark problems of the cosmological constant, physicists began searching for a more elegant and dynamic solution, leading them to propose a compelling alternative. This fourth mystery suggests dark energy might not be a static feature of space, but something far more fluid and changeable, a cosmic field that has been evolving since the dawn of time. This concept is known as quintessence, named after the classical term for a fifth, elusive element beyond Earth, air, fire, and water. Unlike Einstein's constant, quintessence is theorized to be a dynamic scalar field permeating all of space. A scalar field simply means it has a value, a strength, at every point in the universe, but no specific direction, much like a temperature map. This field isn't constant. Its energy density can change over time, gradually rolling down a potential energy slope towards its minimum state. This dynamic nature offers a tantalizing potential solution to the staggering coincidence problem. If the energy density of dark energy is not fixed but instead evolves, it could explain why we find ourselves in this special era where matter and dark energy densities are comparable. In the early universe, the quintessence field could have been sitting high up on its energy hill, its density dwarfed by the overwhelming concentration of matter and radiation. For billions of years, it would have lain dormant, its repulsive effect negligible while gravity ruled the cosmos. Then, as the universe expanded and matter diluted, the field could have begun to slowly roll down, its energy density gradually increasing until it finally became the dominant force, initiating the accelerated expansion we observe today. In this scenario, the timing isn't a bizarre coincidence. It's a natural consequence of a physical process unfolding over cosmic epochs. We aren't living at a miraculously special time. We are simply living at the time when this particular field has finally come into its own. The behavior of this field is often described by an analogy to a ball rolling down a gentle, sloping hill. If the hill is very steep, the ball picks up speed quickly and races to the bottom. But if the hill is incredibly shallow and flat, the ball moves with an almost imperceptibly slow creep, its energy changing very gradually. For quintessence to match our observations, the field must be on an exceptionally flat potential, rolling so slowly that its energy density has only recently begun to overtake that of matter. This slow roll condition is crucial, and it's one of the theory's biggest challenges, as such flat potentials require incredibly fine-tuned conditions to remain stable against quantum fluctuations. Perhaps the most profound aspect of quintessence is its potential to unite the disparate forces of nature. Throughout physics, scalar fields have a celebrated history of solving major cosmic puzzles. The inflatoned field is believed to have driven a period of hyperfast expansion, called inflation, in the universe's first fraction of a second, solving problems like why the universe appears so flat and uniform. The Higgs field gives fundamental particles their mass. Could the quintessence field be another manifestation of this powerful physical concept? Some theoretical models even suggest a deep connection between quintessence and the inflattened field, proposing that dark energy is not a new entity at all, but rather the inflattened field reawakening after a 14 billion-year slumber. Others speculate a link to string theory, where numerous scalar fields could emerge from the complex geometry of hidden extra dimensions. This offers the breathtaking possibility that dark energy isn't an isolated anomaly, but is intimately tied to the most fundamental workings of the universe, a single thread woven through the entire tapestry of cosmic history from the first moment to the last. Yet for all its elegance, quintessence remains a hypothetical idea, a ghost in the machinery of our equations. The true test will come from increasingly precise astronomical observations. By measuring the expansion history of the universe with extreme accuracy, cosmologists hope to detect any minute change in the strength of dark energy over time. A perfectly constant energy density would point firmly back to Einstein's cosmological constant. But if the data ever reveals a subtle shift, a hint that the repulsive force was slightly weaker in the past, it would be a monumental discovery, shaking the foundations of cosmology and opening the door to a universe governed by a dynamic and evolving fifth force. This pursuit of a fundamental explanation for dark energy leads us to one of the most debated and mind-expanding ideas in modern physics, a concept that pushes the very boundaries of what we consider science. This is the fifth mystery, the profound and controversial connection between dark energy, string theory, and the multiverse. To understand this, we first have to venture into the incredibly complex world of string theory itself. This theoretical framework proposes that the fundamental building blocks of nature are not point-like particles but tiny, vibrating strings. The way these strings vibrate dictates the properties of the particles they manifest: an electron, a quark, or a photon. For this elegant mathematics to work, however, the theory requires something our everyday experience doesn't account for: extra dimensions of space. Beyond the three we know, length, width, and height, string theory suggests there could be 6 or 7 more, all curled up into a shape so small we can't perceive them. This is where the landscape emerges. The specific way these extra dimensions are curled and folded is known as the vacuum state, and it determines the laws of physics that would govern a universe constants like the strength of gravity or the mass of an electron. For decades, physicists hoped there would be one unique, mathematically beautiful solution, one specific way for the dimensions to curl that would predict a universe exactly like our own, complete with its measured value of dark energy. But that's not what they found. Instead, the mathematics of string theory points to a staggering number of possible solutions. Current estimates suggest there could be 10 to the power of 500 different possible vacuum states. That number is so incomprehensibly large it dwarfs the number of atoms in the entire observable universe. Each one of these vacuum states corresponds to a universe with a different set of physical laws and constants. This is the string theory landscape, a vast, perhaps infinite, array of possible universes. This is where the anthropic principle, which we encountered with the coincidence problem, returns with a vengeance. If there are 10 to the power of 500 different universes, each with a different value for the strength of its dark energy, then our existence immediately explains why we measure the value we do. In the vast majority of these universes, the dark energy value is likely too large. In those worlds, the repulsive force would have kicked in immediately after the Big Bang, accelerating the expansion so violently that no galaxies, stars, or planets could ever form. It would be a barren, empty cosmos. In another large subset of universes, the value might be 0 or negative, leading to a universe that collapses back in a big crunch long before life can arise. We could only ever find ourselves living in one of the rare, exceptionally fine-tuned universes where the dark energy value is small enough to allow for the formation of large-scale structures and the evolution of life. Our measured value isn't a miraculous coincidence, it's a selection effect. We are here because this is one of the few places that could support our existence. For some physicists, this landscape paradigm is a brilliant and perhaps inevitable conclusion, offering a powerful explanation for fine-tuning without invoking a divine architect or a single, inexplicably perfect universe. It reframes the question from, why are the constants of nature so perfectly set for life, to, in a multiverse where constants vary, what are the conditions necessary for observers like us to emerge? This approach has even made a specific prediction that the value of dark energy should be small but not zero, and that it should be constant predictions that, so far, align with our observations. However, this multiverse explanation is also the source of intense scientific controversy and deep philosophical unease. Critics argue that it risks making physics untestable and unscientific. If every possible physical constant exists somewhere in the multiverse, then we can always explain away any measurement in our universe by saying, well, it had to be that way for us to be here. This can be seen as a form of surrender, a retreat from the traditional goal of physics to find a unique, predictive, and fundamental theory of everything. How do you test for the existence of other universes that are, by definition, beyond our observational reach? Detractors worry that the multiverse concept moves from the realm of empirical science into the domain of metaphysics, interesting philosophy, but not provable physics. The debate is far from settled. It represents a fundamental schism in how scientists view their quest to understand reality. On one side is the hope for a unique, elegant, and final theory that perfectly predicts our universe. On the other is the acceptance of a vast, chaotic multiverse where our universe is just one average island among a countless number, its properties explained not by fundamental law but by mere circumstance. The mystery of dark energy sits right at the heart of this conflict, its faint whisper forcing us to ask not just what the universe is made of, but whether our universe is all there is. And just when we thought the picture of our expanding universe was coming into focus, a new and persistent anomaly has emerged, shaking the very foundations of modern cosmology and suggesting that our understanding of dark energy might be missing a crucial piece. This is the sixth mystery, known as the Hubble tension. At its heart is a deceptively simple question: how fast is the universe expanding right now? The answer, measured in kilometers per second per megaparsec, is known as the Hubble constant. You might think that with all our advanced technology, nailing down this single number would be straightforward. But instead, it has become one of the most significant and stubborn problems in all of astrophysics. Scientists have two primary and seemingly equally trustworthy methods for measuring this expansion rate. The first method looks at the late universe, the cosmic neighborhood relatively close to us in both space and time. Astronomers use what are called standard candles, objects with a known intrinsic brightness like type 1, a supernova, or pulsating stars called Cepheid variables. By measuring how bright these objects appear from Earth and knowing how bright they actually are, we can calculate their distance. Combining this with measurements of how fast they are moving away from us gives us a direct, local measurement of the Hubble constant. This is like measuring the current speed of a car by looking at its taillights right now. The second method looks back to the very early universe using the cosmic microwave background radiation, the faint afterglow of the Big Bang, imprinted when the universe was just 380,000 years old. The Planck satellite provided an exquisitely detailed map of this ancient light. By applying our extremely well-tested standard model of cosmology, which includes specific assumptions about dark energy and dark matter, we can use the patterns in this light to predict what the Hubble constant should be today. This is like calculating how fast that car should be going now based on a precise measurement of how hard its accelerator was pressed seconds after it left the factory. Both methods are incredibly sophisticated, backed by Nobel Prize-winning science, and have been refined to an astonishing degree of precision. And that's precisely what makes the results so deeply troubling. They don't agree, The local late universe measurements consistently give a higher value for the Hubble constant than the early universe prediction from the CMB. The discrepancy isn't a small, negligible margin of error that can be brushed aside. It's a persistent gap of around 4 to 6 kilometers per second per megaparsec, a difference that has only grown more significant as our measurements have become more and more precise. The uncertainty on each measurement has shrunk to such a tiny window that there is now virtually no overlap between them. This isn't a case of fuzzy data, it's a clear and glaring contradiction. This tension suggests a profound possibility that our standard cosmological model, known as lambda CDM, which has been so successful at explaining a vast array of cosmic phenomena, might be incomplete. The model assumes that dark energy is the simple, unchanging cosmological constant. But what if it isn't? The Hubble tension could be the first strong observational hint that dark energy is not constant but dynamic. Perhaps it has evolved over time, changing strength in a way that the standard model doesn't account for. Some theories propose that dark energy could interact with dark matter, a secret dialogue between the two dominant yet invisible components of the cosmos that subtly alters the expansion history. Other ideas suggest that the very nature of dark energy could be more complex than a simple constant, something akin to the quintessence field we discussed earlier, which would change the extrapolation from the early universe to the present day. There are even more radical proposals. Could there be an entirely new type of particle or energy field that we haven't yet accounted for? Might our understanding of gravity itself require modification on the largest cosmic scales, a crack in the flawless edifice of Einstein's general relativity? The Hubble tension forces us to confront these extraordinary possibilities. It's a cosmic detective story where two of our best witnesses are providing sworn testimonies that directly contradict each other. In any good mystery, that doesn't mean one witness is lying. It means there's a deeper truth lurking beneath the surface that we haven't yet uncovered. This discrepancy isn't a failure of science. It's an exciting, if daunting, invitation to discover something new, a signal that the universe still holds profound secrets about its own expansion and the mysterious dark energy driving it. Yet another possibility pushes the boundaries of cosmology even further, challenging one of the most fundamental assumptions we have about the universe, that on the largest scales it is smooth and uniform. This is the cosmological principle, the idea that there is no special place in the cosmos, and that if you look at a sufficiently large volume of space, it will look the same everywhere. But what if that's not true for our entire observable universe? What if we, the Milky Way galaxy, are sitting in the center of a vast billion light-year-wide cosmic void, a region of space with a significantly lower density of matter than the cosmic average? This radical idea forms the seventh mystery, suggesting that the effects we attribute to dark energy might not be caused by a mysterious force at all, but could instead be a grand illusion born from our unlucky location. To understand how this could work, we need to think about gravity and density. According to Einstein's theory, regions with higher density have stronger gravitational pull, which slows down the expansion of space within them. Conversely, regions with lower density have weaker gravity, allowing space within them to expand faster. Now, imagine our local group of galaxies is situated inside a gigantic bubble of below-average density. The space inside this void would be expanding faster than the space outside in the denser regions. From our perspective inside the bubble, it would look as if the entire universe is accelerating in its expansion. We would measure distant supernova to be dimmer than expected, misinterpret that as an accelerating expansion driven by dark energy, and never realize that the answer might be as simple as us living in a slightly emptier than average neighborhood. This idea, known as the void model or the Lemaitre-Tolman-Bondi model, is a compelling and elegant alternative. it does away with the need for dark energy entirely, replacing it with a straightforward, if startling, geometric explanation rooted in well-understood gravity. But this simple solution comes with an enormous cost. It requires us to abandon the cosmological principle. We would have to be living in a truly special and privileged place, right near the center of this giant void, to see the universe the way we do. This directly contradicts the Copernican principle, the cornerstone of modern cosmology, which states that we do not occupy a special or central location in the universe. Proposing that we are at the center of the largest structure imaginable feels, to many scientists, like a return to a pre-Copernican, Earth-centered view of the cosmos. The viability of this model hinges on the size and depth of the proposed void. To explain the observations without dark energy, the void would have to be unimaginably vast, perhaps over 1 billion light-years across, and our galaxy would need to be positioned very close to its center. For a long time, such a structure was thought to be implausible within our standard model of the universe, which predicts a certain statistical distribution of galaxies and clusters. Finding a void that large and that empty would be like finding a single, perfect square mile of completely flat land in the middle of the Himalayan mountains. It goes against everything we understand about how matter clumps together. However, some large-scale galaxy surveys have indeed mapped out enormous underdense regions like the KBC void, which is roughly 2 billion light-years wide and appears to contain our local galactic neighborhood. While its measured density might not be low enough to fully account for dark energy, its mere existence keeps the possibility alive and forces cosmologists to take the idea seriously. The ultimate test for this radical hypothesis will come from a new generation of astronomical instruments. Upcoming galaxy surveys, like those from the Dark Energy Spectroscopic Instrument and the Euclid Space Telescope, are designed to map the three-dimensional distribution of galaxies and matter across the universe with unprecedented precision and depth. They will create a cosmic cartography project of staggering scale, charting the positions of tens of millions of galaxies. These detailed maps will allow scientists to measure the true statistical distribution of voids and filaments in the cosmic web. If we are in a giant void, these surveys should be able to detect its signature unmistakably. They could reveal a specific pattern in the way galaxies move, flowing away from the underdense center and toward the denser walls of the structure, a motion known as a bulk flow. If such a flow is detected on a 1 billion light-year scale, it would be revolutionary evidence for the void model. If it is not found, and the universe appears statistically uniform on the largest scales, it would be a powerful confirmation of the cosmological principle and a significant blow to this alternative explanation for dark energy. Either result is profound. One path leads us to a universe where dark energy is an illusion, but our place in it is bizarrely special. The other path reinforces the standard model, but leaves us still searching for the true nature of the mysterious force that dominates our cosmos. This mystery forces us to question not just what the universe is made of, but also the most basic assumptions we make about its shape and our place within it. But as we venture deeper into the theoretical landscape, we encounter a powerful set of ideas that threaten to upend our most comfortable assumptions. This is the eighth mystery, a confrontation between the pristine mathematics of string theory and the messy reality of our observations, a battle taking place in what theorists call the swampland. The term itself paints a vivid picture. According to this framework, the space of all possible quantum field theories can be divided into two domains. On one side is the landscape, the high ground of consistent, effective theories that can potentially be derived from a complete theory of quantum gravity, like string theory. On the other side is the swampland, a murky bog of theories that might seem perfectly valid on their own, but which fundamentally cannot be connected to a theory of quantum gravity. They are, in essence, mathematical dead ends, disconnected from the ultimate laws of the universe. A series of conjectures, known collectively as the swampland conjectures, act as a bridge between these two domains. They are a set of proposed criteria that any effective field theory must satisfy to be considered part of the consistent landscape and not banished to the swampland. And it is here that we find a direct and dramatic challenge to the cosmological constant. One of the most influential of these is the de Sitter conjecture. It posits that stable, metastable vacuum states with a positive cosmological constant, exactly the type that would describe our universe with its gentle, constant dark energy, simply cannot exist within a complete theory of quantum gravity. In simpler terms, string theory, in its current understanding, may fundamentally forbid a universe that looks like ours with a simple, unchanging dark energy. The mathematics suggests that such a state is unstable and would inevitably decay, placing it firmly in the swampland. If this conjecture holds true, the implications are staggering. It would mean that Einstein's cosmological constant, the simplest and most observationally supported explanation for dark energy, is mathematically forbidden by our best candidate for a theory of everything. Our entire standard model of cosmology, lambda CDM, would be built on a foundation that is fundamentally inconsistent with quantum gravity. This isn't a minor adjustment, it's a conceptual earthquake that would force a complete rewrite of our understanding of cosmic acceleration. The swampland conjectures don't just leave us with a problem, they point toward a specific solution. They strongly favor dynamic models of dark energy like Quintessence, where the energy density evolves over time. In particular, they suggest that for a theory to remain out of the swampland, the value of the dark energy field must change over a certain distance in field space, and its potential energy must be steep enough to avoid the stability problems of a pure vacuum energy. This creates a clear, testable prediction that the equation of state parameter W should not be exactly -1, but should be detectably different, perhaps closer to -0.9. This is where the tension with observation becomes white-hot. Our most precise measurements of the cosmic microwave background and distant supernova consistently point to a value of W being extremely close to -1, perfectly consistent with a cosmological constant. The error bars are getting smaller and smaller, and so far, they show no definitive sign of the deviation that the swampland conjectures seem to require. We are left with a profound dilemma. Is our observational data not yet precise enough to detect the subtle dynamics that quantum gravity demands? Or are the swampland conjectures themselves incorrect, or perhaps not as universal as their proponents believe? This standoff is more than just an academic debate. It is a direct clash between the top-down approach of theoretical physics, deriving constraints from the presumed laws of quantum gravity, and the bottom-up approach of observational cosmology, building models from what we actually see in the sky. The outcome of this struggle will reshape fundamental physics. If future observations, perhaps from the Nancy Grace Roman Space Telescope or the Vera C. Rubin Observatory, finally detect a clear deviation from W equals -1, it would be a monumental victory for the swampland ideas and a giant leap toward validating string theory as the correct framework for nature. It would mean that dark energy is not a constant but a dynamic field, and that the universe is governed by laws that deeply connect the infinitesimally small world of strings to the impossibly large scale of the cosmic horizon. Conversely, if observations continue to tighten the noose around W equals -1, it would pose a serious crisis for string theory as it is currently understood, potentially forcing a major revision of its core principles or even sending physicists back to the drawing board in their quest for quantum gravity. The swampland conjectures have turned the mystery of dark energy into a high-stakes testing ground, where the fate of our most ambitious theoretical ideas will be decided by the cold, hard light of the stars. This journey through the cosmic implications of dark energy now brings us to a mystery that is perhaps the most abstract and philosophically profound of all, one that pits the relentless expansion of the universe against the most fundamental laws of quantum physics. This is the ninth mystery, the ultimate fate of information itself. To grasp why this is such a deep puzzle, we need to revisit a cornerstone of quantum mechanics, the principle that information cannot be created or destroyed. It can change form, be scrambled beyond recognition, but it is never truly lost. Think of it this way. If you were to burn a book, the pages turn to ash and smoke, seemingly erasing the story. But in principle, if you could track every single particle of ash and wisp of smoke, accounting for their exact positions and energies, you could theoretically reverse the process and reconstruct the book. The information about its text was never destroyed, it was just transformed into a far more complicated state. This principle is famously tested in the black hole information paradox. When something falls into a black hole, it seems to be lost forever, its information trapped behind an event horizon from which not even light can escape. But Stephen Hawking showed that black holes slowly evaporate over astronomical timescales through a quantum process, eventually radiating away all their mass as a featureless glow of Hawking radiation. The terrifying question became, when the black hole is gone, what happened to the information of all the things that fell in? Was it truly destroyed, violating quantum law, or is it somehow encoded, impossibly scrambled in that outgoing radiation? This paradox has driven theoretical physics for decades, and most physicists believe a solution exists where information is preserved, even if we don't yet fully understand the mechanism. Now scale this problem up to the entire cosmos, a universe dominated by a cosmological constant, expanding at an accelerating rate, creates a different kind of horizon. It's not the gravitational barrier of a black hole, but a cosmological event horizon, because the expansion between two distant points in space can eventually exceed the speed of light. There is a limit to what we can ever observe or interact with in the far future. Galaxies beyond a certain distance will be pushed away so quickly that their light will never, ever reach us. They cross over our cosmological horizon and are effectively lost to our view forever. As this acceleration continues, the universe becomes increasingly empty and isolated. Eventually, every single galaxy, every star system, will be alone in its own observable universe, surrounded by an impenetrable darkness, completely causally disconnected from everything else. Now, here is the cosmic scale information paradox. Imagine a future historian on a world in one of those isolated galaxies. They want to know about the early universe, about the Big Bang, about the formation of the first galaxies. But they can't. All of that evidence, all of those photons carrying that historical information, have been redshifted into oblivion or have passed beyond their cosmological horizon. That information is not just practically inaccessible. According to our best models, it is fundamentally inaccessible, lost behind a horizon that is every bit as real as the one around a black hole. This presents a philosophical nightmare. If those regions of the universe and the information they contain are forever beyond any possible observation or interaction, can we meaningfully say they still exist? And if that information is functionally lost to any observer, does this constitute a violation of the quantum mechanical law that information must be preserved? We are left with two deeply unsettling options. The first is that quantum mechanics is wrong, and information can be destroyed on a cosmic scale, which would require a complete overhaul of the most successful fundamental theory in all of physics. The second, even more mind-bending option is that the information isn't truly lost. Perhaps it is somehow preserved on or encoded at the cosmological horizon itself, a holographic projection of a higher dimensional reality, much like some proposed solutions to the black hole paradox. This isn't just an academic exercise, it strikes at the heart of what reality is and what physics can ultimately explain. It suggests that the accelerated expansion driven by dark energy doesn't just dictate the future of matter and energy, but the future of knowledge and causality itself, potentially creating a universe where the complete history of existence becomes unknowable, fractured into an infinite number of isolated pockets, each with only a fragment of the whole story. The mystery of dark energy thus becomes inextricably linked to the mystery of how the universe remembers itself, and whether the cosmos will ultimately preserve its own history or allow it to fade into nothingness. At the very heart of the quest to unmask dark energy lies a single, crucial number, a parameter so fundamental that its precise value could rewrite our textbooks. This is the equation of state denoted by the letter W. It's the key that could finally unlock whether dark energy is a simple, static cosmological constant or a dynamic, evolving force. Think of W as the fingerprint of dark energy, a unique identifier that describes the relationship between its pressure and its energy density. For a pure cosmological constant, this value is perfectly and eternally -1. It's a fixed setting on the cosmic control panel, a constant whisper of repulsive gravity that has remained unchanged since the beginning of time. But if W is not exactly -1, or even more intriguingly, if it changes over time, then everything we think we know gets turned on its head. A value that differs from -1 even by a tiny amount would be the smoking gun for a dynamic theory like quintessence. It would tell us that dark energy isn't a feature of the vacuum itself, but something more like a field that can weaken or strengthen, a fifth force rolling down its own energy landscape. The most exciting possibility is if W evolves, meaning it had a different value in the past than it does today. Detecting that temporal shift would be like finding a fossilized dinosaur bone. It would provide direct evidence that dark energy has a history, a story that has been unfolding for billions of years alongside the galaxies and stars. Measuring this parameter with the required exquisite precision is one of the greatest technical challenges in all of modern cosmology. You can't just point a telescope at a patch of empty space and measure W directly. Instead, astronomers have to become cosmic detectives, piecing together its value by painstakingly reconstructing the entire expansion history of the universe. They use multiple, independent lines of evidence, each acting as a cross-check on the others. The primary method involves looking back in time with standard candles, particularly Type 1, a supernova. By measuring the brightness of these supernovae at different distances, and therefore different epochs in cosmic history, scientists can trace how the expansion rate has changed over billions of years. Any deviation from the expected acceleration predicted by a simple cosmological constant would immediately show up as a variation in W. Another powerful technique involves mapping the large-scale structure of the universe. As the universe expanded, gravity pulled normal matter and dark matter together into a vast cosmic web of clusters, filaments, and voids. But dark energy works against this clustering, suppressing the growth of these structures. By meticulously measuring the distribution of galaxies and the subtle distortions in the light from distant galaxies caused by gravitational lensing, scientists can infer the strength of dark energy's repulsive push throughout cosmic history. The size of the Barrian acoustic oscillations, frozen sound waves from the early universe imprinted in the distribution of galaxies, acts as a standard ruler. Measuring how this apparent size changes with distance gives us another precise yardstick for the universe's expansion, further constraining the value of W. This is where a new generation of astronomical observatories comes in, instruments so powerful they are essentially time machines designed to solve this specific mystery. The European Space Agency's Euclid Space Telescope and NASA's upcoming Nancy Grace Roman Space Telescope are not just upgrades, they represent a quantum leap in our observational capabilities. Euclid, with its incredibly wide field of view, is conducting a massive survey of the sky, measuring the shapes and redshifts of over 1 billion galaxies. This will create an unprecedented 3D map of the cosmic web, allowing scientists to trace the imprint of dark energy on the growth of structure with phenomenal detail. The Roman Space Telescope will perform its own vast surveys, discovering thousands of new distant supernovae to chart the expansion history with finer granularity than ever before. The goal of these missions is not just to measure W more accurately, but to finally detect any potential evolution, a parameter often called WA. They are designed to shrink the error bars on these measurements from a few percent down to a fraction of a percent. This level of precision is what's needed to definitively rule entire classes of theories in or out. If, after all this, the data continues to point relentlessly to W being exactly -1 with no evolution, it would be a monumental victory for the cosmological constant, solidifying Einstein's once-rejected idea as a fundamental feature of reality. But if these powerful new eyes on the sky catch even a hint of a deviation, a whisper that W is something like -0.99 and slowly changing, it would ignite a new revolution in physics. It would be the evidence we need to finally move beyond the cosmological constant and start exploring the true, dynamic nature of the dark energy that shapes our cosmic destiny. Just when we thought the cosmic microwave background had given up all its secrets, revealing a near-perfect snapshot of the infant universe, it presented us with an anomaly so strange that scientists named it the axis of evil. This 11th mystery takes us back to that primordial afterglow, not to study its overall uniformity, but to investigate a set of peculiar and seemingly impossible alignments that hint at a cosmic architecture far stranger than we ever imagined. Our story begins with the Wilkinson Microwave Anisotropy Probe, or WMAP, and later the Planck satellite. These missions mapped the CMB in breathtaking detail, measuring tiny temperature fluctuations on the order of 1/100,000th of a degree that represent the seeds of all future structure in the universe. When scientists analyzed this data, they expected to find a random Gaussian distribution of these hot and cold spots, a fingerprint of the uniform, isotropic universe predicted by the Standard Model. For the most part, that's exactly what they found. But when they looked at the very largest scales at the patterns known as the low multipoles, specifically the quadrupole and octupole moments, something was deeply off. Instead of being randomly oriented, the hot and cold spots on these colossal scales appear to be aligned. Their axes are not pointing in arbitrary directions, they seem to be correlated with each other. Even more bizarrely, this preferred axis, this so-called axis of evil, shows a startling and deeply suspicious alignment with our own solar system. It lines up closely with the ecliptic plane, the imaginary disk in which the planets orbit the Sun, and even shows a connection to the equinoxes. This is profoundly unsettling. It's as if the largest scale structure of the entire observable universe is somehow aware of the utterly insignificant orientation of our tiny little solar system. The probability of this happening by pure chance is incredibly low, leading some researchers to suggest the unthinkable, that we might be seeing the shadow of a fundamental cosmic anisotropy, a preferred direction in the fabric of space-time itself. The immediate and most conservative explanation is systematic error. Perhaps the signal isn't from the cosmos at all, but is an artifact generated by our own instruments or by the local environment of our galaxy. Maybe dust in the solar system or an unaccounted-for foreground emission from the Milky Way is contaminating the data and creating this illusory alignment. Scientists have spent years meticulously checking and rechecking the data from both WMAP and Planck, subtracting every conceivable source of interference. And yet, the anomaly stubbornly persists. It hasn't gone away. This resilience is what transforms it from a potential date, a glitch, into a genuine cosmic mystery. If it's not an error, the implications are staggering. It would mean the cosmological principle, the foundational idea that the universe is homogeneous and isotropic on large scales is not entirely correct. There could be a fundamental lopsidedness to the universe, a grand cosmic architecture with a preferred axis. This is where the connection to dark energy emerges from the theoretical shadows. Some cosmologists have proposed that this alignment isn't a fossil from the beginning of time, but a dynamic effect imprinted much later. What if the repulsive force of dark energy isn't perfectly uniform? Could it be slightly stronger in one direction than in others? This kind of anisotropic dark energy would not only accelerate the expansion of the universe, but could also tug on the very fabric of space-time, warping it on the largest imaginable scales and creating a subtle directional preference that we see echoed in the CMB. This idea pushes the boundaries of our models to the breaking point. It suggests that the force dominating the universe could be more complex than a simple, smooth fluid, perhaps a field with variations or textures woven through the void. Alternatively, the axis of evil might not be about dark energy directly, but could be a window into the epoch of inflation, the universe's hyper-fast expansion in its first fraction of a second. Perhaps the initial conditions set by inflation were not perfectly uniform, and this alignment is a rare, frozen relic of that primordial epoch, a cosmic fossil that somehow survived 14 billion years of evolution. Resolving this mystery is one of the foremost challenges in modern cosmology. It sits at the treacherous intersection of undeniable data and profound theoretical discomfort. It forces us to ask whether we are seeing a ghost in our own machine or the first faint glimpse of a universe that is fundamentally oriented, a cosmos with a north and south on a scale beyond human comprehension. The answer, whatever it may be, promises to either clean up a persistent thorn in the side of our standard models or tear those models down completely, forcing us to build a new understanding of the universe that includes, for the first time, a direction to the heavens. Now, just when we thought we'd exhausted all the obvious possibilities, a theory emerges from the intersection of quantum physics and cosmology that offers a radically different perspective. This is the 12th mystery, the running vacuum model. What if the density of dark energy isn't a true constant, and it isn't a rolling field either, but something far more subtle, a value that slowly runs, evolving in tandem with the expansion of the universe itself? This idea doesn't just tweak the cosmological constant, it fundamentally reimagines it as a dynamic entity connected to the very energy scale of the cosmos. To understand this, we need to take a quick detour into the world of quantum field theory, the framework that describes how particles and forces interact. In this realm, there's a powerful mathematical tool known as the renormalization group. This isn't a social club for physicists. It's a formal way of understanding how the strength of forces and the values of constants can actually change depending on the energy scale you're looking at. For instance, the electromagnetic force behaves slightly differently at the energy levels inside a massive star than it does here on Earth. The constants aren't broken, they're just context-dependent. The running vacuum model applies this exact same principle to the entire universe. It proposes that the cosmological constant, lambda, isn't a fixed number etched into the fabric of reality, but a parameter that runs with the energy scale of the universe, which is directly tied to the Hubble rate, the rate of the universe's expansion. Think of it like this. Imagine the universe is a vast cooling engine. In its earliest, hottest, and most energetic moments right after the Big Bang, the vacuum energy was at its peak. But as the universe expands and cools, its overall energy density drops. The running vacuum model suggests that the energy density of the vacuum itself isn't immune to this cosmic cooling trend. It slowly decreases alongside everything else, diluting as the cosmos grows. In this view, dark energy isn't a separate, mysterious force fighting against gravity. It's an integral part of the cosmic fluid. its strength subtly diminishing over billions of years in a precise, predictable way governed by the laws of quantum field theory. This elegant idea has a breathtaking payoff. It potentially solves not one, but two of our biggest problems in a single stroke. First, it directly addresses the cosmological constant problem, that staggering discrepancy of 120 orders of magnitude. In this model, the vacuum energy isn't a colossal, static number that somehow magically cancels itself out. Instead, it starts from a more natural, physically plausible value in the early universe and then naturally runs down to the incredibly small, non-zero value we measure today. The number isn't fine-tuned. It's a natural consequence of the universe's evolution and cooling. Second, it offers a compelling solution to the coincidence problem, the puzzle of why we live in the special era when matter and dark energy densities are comparable. If dark energy's density has been slowly decreasing over time, while matter's density has been rapidly diluting due to expansion, their lines were destined to cross at some point. It wasn't a random, miraculous coincidence. It was an inevitable meeting on a cosmic timeline. In the distant past, matter dominated because the running vacuum energy, while larger than today, was still overshadowed by the incredible density of particles. In the far future, the running vacuum will become the dominant remnant because matter will have diluted away to almost nothing. We find ourselves at the crossroads not by accident, but as a natural outcome of this gradual evolutionary process. The running vacuum model is a powerful and compelling synthesis, weaving together the quantum world with the cosmic scale. It treats the universe not as a static stage with fixed constants, but as a dynamic, evolving system where even the laws themselves breathe and change along with the expansion. It's a theory that respects the machinery of quantum field theory while providing elegant, natural solutions to cosmology's most vexing puzzles. Of course, it is not without its own challenges and requires precise observational testing, but it stands as a brilliant testament to the creativity of physicists who refuse to accept that the deepest mysteries of the cosmos are simply unsolvable paradoxes. Now we turn to a mystery that connects the very largest scales of the cosmos to the very first minutes of its existence, linking the enigma of dark energy to a long-standing problem buried deep in the periodic table. This is the 13th mystery, an investigation into the curious case of the missing lithium and its potential, though controversial, connection to the force shaping our universe's future. To set the stage, we need to travel back to an era known as Big Bang nucleosynthesis, or BBN. This was the universe's first few minutes, a frantic and blisteringly hot period when the entire cosmos was a seething nuclear fusion reactor. During this brief window, the primordial soup of protons and neutrons collided and fused, cooking up the very first atomic nuclei: hydrogen, helium, and trace amounts of lithium and beryllium. For decades, our mathematical models of BBN have been exquisitely precise, able to predict the exact abundances of these elements we should find in the oldest parts of the universe. And for the most part, they've been spectacularly successful. The predicted amounts of hydrogen and helium match the observed amounts in ancient, pristine gas clouds with near-perfect accuracy, a triumph for the Big Bang theory. But there is one glaring, persistent exception: lithium. The models predict that the primordial abundance of lithium-7 should be about 3 to 4 times higher than what astronomers actually measure when they look at the atmospheres of the oldest stars in our galaxy. These ancient suns, population 2 stars, formed from material that was never polluted by later generations of supernova, so their chemical composition is a frozen record of the early universe. And consistently, their lithium levels are far lower than our theories say they should be. This isn't a small margin of error. It's a significant discrepancy that has stubbornly resisted explanation for over 30 years. Scientists have proposed all sorts of solutions, from novel nuclear reaction rates to the possibility that these ancient stars have somehow destroyed or diluted their lithium over billions of years. but no conventional astrophysical fix has fully resolved the issue. This is where the connection to dark energy emerges from an unexpected direction. What if the solution isn't in the stars themselves, but in the very laws of physics that govern that primordial fusion reactor? Some theoretical cosmologists have proposed that the gravity we use to model the extreme conditions of the early universe might be incomplete. Our standard BBN calculations rely on Einstein's general relativity operating exactly as it does today. But what if gravity behaved slightly differently in that incredibly dense, hot environment of the first few minutes? This idea, known as modified gravity, is often explored as an alternative to dark energy on cosmic scales. But its effects could also reach back in time to alter the expansion rate of the universe during those critical first minutes. This is the crucial link. The outcome of Big Bang nucleosynthesis is exquisitely sensitive to the expansion rate of the universe. The faster the universe expands during those first few minutes, the less time protons and neutrons have to find each other and fuse into heavier elements. A tiny change in the expansion rate can dramatically alter the final abundances, especially for delicate isotopes like lithium-7. Now, consider one of the leading alternative explanations for dark energy, early dark energy models. These theories propose that a form of dark energy, perhaps a cousin to quintessence, was not just present but was actually dominant in the very early universe during that BBN epoch. This early dark energy would have caused a temporary, extra burst of expansion, a slight speed up during the universe's first few minutes before it quickly faded away. This subtle tweak to the cosmic expansion history could be the key that unlocks both mysteries. An episode of early dark energy would have made the universe expand just a little bit faster during BBN. This would have shortened the window for nuclear fusion, potentially reducing the amount of lithium-7 that was produced, thereby bringing the theoretical predictions into line with the frustratingly low observed values. In this elegant scenario, a single theoretical adjustment, a dynamic form of dark energy active in the universe's infancy, could simultaneously explain the acceleration we see today and correct a 50-year-old problem in our understanding of the universe's first elements. It's a breathtakingly beautiful proposition that the force which is currently ripping the cosmos apart also played a subtle, defining role in its elemental composition, leaving a faint fingerprint in the lithium content of the oldest stars. However, it's important to note that this connection remains highly speculative and is far from being the mainstream consensus. The lithium problem is a complex astrophysical puzzle with many potential solutions, and pinning it directly on early dark energy is a bold claim that requires extraordinary evidence. Yet, it exemplifies the kind of deep, cross-disciplinary thinking that modern cosmology demands. It forces us to see the universe not as a collection of isolated events, but as a single, interconnected system where a phenomenon affecting the largest scales today might have left its signature on the smallest scales at the very dawn of time. Solving the mystery of the missing lithium might not just fill a page in a chemistry textbook. It could provide a critical clue in our quest to understand the dark energy that governs everything. What if we've been making a fundamental mistake in our cosmic accounting, mistakenly counting one mysterious entity as two? This 14th mystery takes us down a path of radical simplification, exploring a concept so elegant it feels almost too good to be true: the Chaplygin gas. Imagine a single, exotic substance that could wear two completely different masks, acting as the gravitational glue of dark matter in the universe's youth before transforming into the repulsive force of dark energy in its old age. This isn't just a convenient fantasy. It's a serious, mathematically beautiful model that proposes a unified solution to the two greatest mysteries in cosmology, potentially solving the profound coincidence problem in the process. The story begins not in a modern physics lab, but in the early 20th century with a Russian physicist named Sergei Chaplygin. He was studying aerodynamics and derived the equations for a hypothetical fluid with a truly bizarre property. Its pressure is inversely proportional to its density. This means that when this gas is squeezed and becomes very dense, its pressure doesn't skyrocket like a normal gas. Instead, it becomes more negative, generating a sort of suction or tension. For decades, this was little more than a mathematical curiosity. Then, cosmologists searching for alternatives to the standard model realized that this unusual pressure-density relationship could have a stunning cosmic application. In the context of cosmology, this Chaplygin gas becomes a candidate for a unified dark sector. Picture a single fluid permeating all of space. In the early, dense universe, this fluid would have a high density but a pressure very close to zero. This near-zero pressure means it wouldn't experience the kind of pressure support that would prevent it from clumping together under gravity. Just like cold, dark matter, it would collapse to form the gravitational scaffolding for galaxies and clusters. It would behave exactly as we observe dark matter to behave, but as the universe expands, the density of this fluid drops, and according to its defining equation, as its density decreases, its pressure becomes increasingly negative. This negative pressure is the hallmark of dark energy, a repulsive force that drives acceleration. So, over billions of years, this single entity seamlessly transitions from acting like dark matter to acting like dark energy. It's a cosmic chameleon, changing its behavior based on the environment of the expanding universe. The elegance of this idea is breathtaking. It dissolves two profound mysteries into one. We no longer have to ask why the universe contains about 5 times more dark matter than normal matter, and why it contains about 3 times more dark energy than dark matter and normal matter combined. There is only one unknown component, the Chaplygin gas, and its evolution naturally produces the observed cosmic history. Most compellingly, it offers a clear and natural solution to the coincidence problem. The reason we see dark matter and dark energy densities that are roughly comparable today isn't a bizarre accident. It's simply because we are living at the precise era when this unified fluid is in the middle of its transition from one state to the other. The timing isn't miraculous, it's inevitable. So why hasn't this beautifully simple model taken over cosmology? The answer lies in the cold, hard light of observational data. As powerful telescopes gathered more precise information about the universe, the Chaplygin gas model began to falter under the weight of evidence. One of the biggest blows came from the study of large-scale structure. The model struggles to simultaneously explain the precise pattern of the cosmic microwave background and the observed distribution of galaxies we see today. The transition from a dark matter-like state to a dark energy-like state happens in a specific way that imprints a signature on how structures form. When astronomers compare these predictions to the actual cosmic web mapped out by galaxy surveys, the two don't align perfectly. The unified fluid tends to suppress the formation of structure slightly too much, failing to create the rich tapestry of clusters and voids that we observe. Furthermore, the model makes specific predictions about the speed of sound waves within this exotic fluid. These predictions often conflict with the constraints we have from observing the CMB, where the transmission of these sound waves in the early universe is frozen in time. The data strongly favors models where dark matter is purely pressureless or cold, and where dark energy is either a constant or a very slowly evolving field. The Chaplygin gas, in its attempt to be both, ends up being less convincing than the two-component model it sought to replace. Despite these observational challenges, the Chaplygin gas has not been completely abandoned. It remains a deeply intriguing mathematical specimen, a prototype for how a unified dark sector could potentially work. Theorists have developed more sophisticated variants like the generalized Chaplygin gas, which introduces more parameters to try and fit the data better. While these adjustments can improve the fit, they also sacrifice the pristine simplicity that made the original idea so appealing. Today, it stands as a fascinating what-if scenario, a testament to the creativity of cosmologists striving for a more elegant universe, and a reminder that sometimes nature's answers are more complex and separate than our desire for simplicity would hope. It challenges us to keep looking for connections, even when the evidence points toward a cosmos built on multiple, distinct, and deeply mysterious foundations. The quest to understand dark energy inevitably forces us to confront the single greatest unsolved problem in all of physics, the profound and seemingly irreconcilable divorce between the two pillars of modern science, quantum mechanics and general relativity. This 15th mystery asks if dark energy itself might be the very key that finally unites these two magnificent but incompatible theories into a single, coherent theory of quantum gravity. The puzzle lies in the impossibly small energy scale of dark energy, a number so tiny it might be pointing toward entirely new principles of nature, perhaps hidden dimensions or undiscovered symmetries that govern the cosmos. To grasp why this scale is so baffling, we need to appreciate how these two great theories view the vacuum of space. In quantum field theory, the vacuum is not empty. It is a seething, frothing sea of virtual particles and fields constantly fluctuating, boiling with an immense energy density. This is the zero-point energy, and our calculations of its strength are based on summing up all the contributions from every possible quantum field up to the highest energy scales we know, like the Planck scale. When we perform this calculation, the result is a number so colossal it would have ripped the universe apart in a fraction of a second after the Big Bang. It's often called the worst prediction in all of physics, off by a factor of 10 to the power of 120 from the observed value. Now switch to the cosmic perspective of general relativity. Here, the vacuum energy manifests as Einstein's cosmological constant, a gentle, constant pressure that drives the accelerated expansion of the universe. The observed value of this energy is almost zero, but not quite. It is a whisper of a force, a faint hum in the background of space-time that only becomes dominant after billions of years of cosmic expansion. This is the staggering discrepancy. The quantum world predicts a raging, infinite ocean of vacuum energy, while the cosmic world observes nothing more than a faint, barely there mist. This isn't just a minor accounting error. It's a screaming contradiction that suggests our understanding of the vacuum is fundamentally flawed. The puzzle of dark energy's scale is that it sits at a precise and seemingly impossible sweet spot. If it were significantly larger, even by a minuscule amount, the accelerated expansion would have begun so early in the universe's history that galaxies, stars, and planets could never have formed. If it were exactly zero, we wouldn't be having this discussion, as the universe's expansion would be gradually slowing down. The fact that it is so small, yet precisely non-zero, is a clue that something profound is canceling out almost all of that quantum vacuum energy, leaving behind just this incredibly tiny residue. This isn't a problem of calculation, it's a problem of principle. It suggests that the true theory of quantum gravity must contain a mechanism, a symmetry, or a principle that naturally forces the cosmological constant to be nearly zero. This is where the most exciting theoretical possibilities emerge. Some physicists, particularly those working on string theory, propose that the answer lies in extra dimensions. In these theories, the gravitational force, and by extension the energy of the vacuum, could be diluted by leaking into these hidden spatial dimensions that are curled up on scales too small for us to perceive. The incredibly weak strength of gravity compared to the other forces might already be a hint of this leakage, and dark energy's faintness could be another manifestation of the same effect. Another compelling idea is the existence of a new, undiscovered symmetry in nature. In physics, symmetries often lead to conservation laws and can force certain quantities to be zero. For instance, supersymmetry, a hypothesized symmetry between particles of force and particles of matter, would naturally cancel out the vacuum energy to exactly zero. However, since we observe a small positive value, supersymmetry, if it exists, must be broken at some scale. The challenge is to find a symmetry, perhaps one we haven't even conceived of yet, that doesn't cancel the vacuum energy completely, but leaves behind the exquisitely tiny remnant we measure as dark energy. This energy scale is so peculiar that it might be pointing toward a cosmic version of the hierarchy problem, which deals with the vast gap between the strength of gravity and the other forces. Dark energy's energy density is 1 billion times smaller than the energy density of a neutrino, which is itself incredibly light. This suggests that whatever principle is at work is operating with an almost unbelievable level of precision and delicacy. Ultimately, dark energy may be more than just a mysterious component of the universe. It could be the most important experimental clue we have in the search for a final theory. Its existence and its specific properties are an anomaly that neither quantum mechanics nor general relativity can explain on its own. It is a phenomenon that lives at the intersection of the incredibly large and the unfathomably small, demanding a theory that can speak the language of both. Unraveling its secret might not just tell us why the universe is accelerating. It might finally provide the Rosetta Stone that allows us to translate between the quantum and the cosmic, revealing a deeper, unified reality hidden beneath. But what if the influence of dark energy isn't a recent development in the cosmic story? What if this mysterious force was not just present, but actually playing a major role during the universe's infancy, leaving its fingerprints on the very first structures to form? This brings us to our 16th mystery, the early dark energy hypothesis, a radical idea that suggests dark energy's performance on the cosmic stage had a powerful opening act billions of years before its current starring role. The standard narrative paints dark energy as a latecomer. For most of cosmic history, the universe was dominated by the gravitational pull of matter and radiation, its expansion gradually slowing down. Dark energy, according to this view, was a background player, its repulsive force too weak to make a difference until the universe had expanded enough for matter to dilute and dark energy's constant density to finally take over. But the early dark energy hypothesis turns this story on its head. It proposes that a form of dark energy was not only present in the first several 100,000 years after the Big Bang, but that it was a dominant component of the cosmos, a temporary but potent force that altered the universe's expansion history during its most formative moments. Why would we entertain such a dramatic revision of the cosmic timeline? The answer lies in those persistent anomalies we've discussed, particularly the Hubble tension. The discrepancy between the early universe and late universe measurements of the expansion rate is a thorn in the side of the standard model. Early dark energy offers an elegant, if speculative, solution. Imagine a new, exotic energy field that existed only for a brief cosmic instant. This field would have injected an extra burst of acceleration into the very early universe, causing it to expand just a little bit faster during the epoch of Big Bang nucleosynthesis and recombination, when the cosmic microwave background was emitted. This would directly affect the physics imprinted on that ancient light. When we use the standard model to extrapolate from that early CMB data to predict the current expansion rate, we get one number. But if an early dark energy field caused a temporary speed up that later vanished, our standard extrapolation would be slightly off. By the time we factor in this early boost, the predicted expansion rate today could align much more closely with the value we measure locally, potentially resolving the tension. The effects of this early push would be profound and far-reaching, leaving subtle but detectable marks on the cosmos. One of the most significant imprints would be on the cosmic microwave background itself. The patterns of hot and cold spots in the CMB are a precise record of acoustic waves, sound waves rippling through the primordial plasma. The scale of these waves is an exquisite standard ruler. An episode of early dark energy would have changed the expansion rate just as these sound waves were traveling, altering their apparent size and the detailed statistical properties of the CMB fluctuations. It would also affect the timing of when the first atoms formed and the universe became transparent, an event known as recombination. Current data from the Planck satellite is already so precise that it places tight constraints on any such deviations from the standard model, but proponents of the idea are actively searching for specific, unique signatures that a brief early dark energy phase would leave behind. Furthermore, this hypothesis has dramatic consequences for the formation of the universe's large-scale structure. The growth of galaxies and clusters is a delicate dance between gravity, which pulls matter together, and the expansion of the universe, which pulls it apart. An early period of accelerated expansion would have acted like a cosmic pause button, briefly suppressing the gravitational collapse of the tiny density fluctuations that were the seeds of future galaxies. This suppression would leave a distinct signature in the distribution of matter we see today. It would affect the timing of when the first stars ignited and how galaxies assembled, potentially offering another avenue to test this idea against observations from the most powerful telescopes. The early dark energy hypothesis is a testament to the creativity of cosmologists faced with stubborn data. It demonstrates a willingness to radically rethink the cosmic narrative to solve fundamental puzzles. However, it is not a theory without its own significant challenges. Introducing a new energy field that is dominant only for a short, early period can feel like adding a complicated epicycle to the model simply to fix one problem. The theory requires a degree of fine-tuning to ensure this early dark energy field decays away at just the right moment, leaving no trace for billions of years until the modern cosmological constant takes over. Despite these hurdles, it remains a compelling and active area of research, a bold suggestion that the key to understanding the universe's present expansion may be hidden in the details of its explosive birth. Now we venture into one of the most abstract and mathematically profound frontiers of theoretical physics, where the enigma of dark energy collides with the fundamental quantum nature of information. This 17th mystery explores a stunning and unexpected connection between the cosmological constant and the infamous black hole information paradox, suggesting that the accelerating expansion of our universe might not be an obstacle to understanding quantum gravity, but the very key that unlocks it. For decades, the black hole information paradox has stood as a monumental challenge. It questions whether the information that describes the quantum state of matter falling into a black hole is truly lost forever when the black hole evaporates through Hawking radiation, which would violate a core principle of quantum mechanics, or if it is somehow preserved, scrambled into the outgoing radiation. Recently, a breakthrough emerged from the study of gravitational path integrals, a powerful, if complex, mathematical technique for calculating quantum gravitational effects. Researchers discovered that to get a sensible answer for the entropy of Hawking radiation, they had to include contributions from regions of spacetime that are disconnected from the black hole itself, strange configurations dubbed quantum extremal islands. These islands, which appear from the perspective of an outside observer to be behind the black hole's event horizon, somehow still manage to encode the information necessary to preserve unitarity, the principle that quantum information cannot be destroyed. This is where dark energy enters the picture in a truly spectacular fashion. The mathematics of these quantum extremal islands isn't exclusive to black holes. It applies to any spacetime with a horizon, including the cosmological horizon created by a positive cosmological constant, the hallmark of dark energy. In a universe like ours, accelerating due to dark energy, every observer is surrounded by a horizon beyond which they can never see or receive information. It's a horizon that encompasses us all, a permanent boundary to our knowledge of the cosmos. The recent theoretical work suggests that this cosmological horizon behaves in a profoundly similar way to a black hole horizon when it comes to quantum information. The same island formula that rescues information from a black hole appears to operate within the framework of an accelerating universe, implying that the vast, empty space beyond our cosmological horizon might be threaded with these quantum islands, quietly preserving the information of everything that has crossed over. This paints an astonishing new picture of our dark energy-dominated fate. Instead of a cold, isolated universe where information is forever lost behind an ever-expanding curtain, we might be living in a cosmos where quantum information is eternally preserved through a complex web of entanglement that connects us to those inaccessible regions via the island mechanism. The cosmological constant, long seen as a simplistic and problematic ingredient in our models, might be an essential feature that allows for a consistent and unitary theory of quantum gravity in an expanding universe. Its presence creates the precise type of horizon necessary for this elegant mathematical solution to work. This turns the traditional view on its head. Dark energy isn't a nuisance. It might be a prerequisite for a cosmos that makes quantum sense from beginning to end. These breakthroughs are deeply tied to our evolving understanding of entanglement in de Sitter space, the mathematical description of a universe with a positive cosmological constant. Entanglement, the spooky action at a distance that links quantum particles regardless of distance, is now seen as the fundamental glue that holds space-time itself together. In de Sitter space, the relentless expansion driven by dark energy constantly stretches and strains these quantum connections. The recent research delves into how entanglement entropy is calculated in this dynamic environment, and the results consistently point back to the necessity of these island contributions to avoid paradoxical contradictions. It suggests that the fabric of our accelerating universe is woven with an intricate, self-correcting quantum code that ensures no information is ever truly lost, even as the cosmos dilutes into emptiness. The very force that is pulling the universe apart might be the very thing ensuring its quantum coherence, a beautiful and paradoxical symmetry at the heart of reality. While the cosmological constant and quintessence rely on adding a new component or field to the universe, what if dark energy isn't something we add, but something the universe itself does as a natural consequence of its own aging? This 18th mystery introduces us to a theory of profound elegance and predictive power, the vacuum metastability event, often poetically termed the false vacuum decay. This idea suggests that what we perceive as dark energy might not be a force at all, but the harbinger of an impending and catastrophic phase transition, a cosmic bubble of true vacuum that could erase the universe as we know it in a flash of reconfiguration. To understand this, we need to think of the universe's vacuum not as empty nothingness, but as a field filled with energy, sitting in a state of stable equilibrium, much like a ball resting at the bottom of a valley. According to quantum field theory, the vacuum we inhabit might not be the true, lowest energy state possible. It could be a false vacuum, a local minimum in the energy landscape. Imagine a ball sitting in a small depression on the side of a much larger hill. It seems stable, but it's not in the true valley far below. It's in a state of metastability. For now, it's secure, but given a big enough push or through the sheer unpredictability of quantum tunneling, it could suddenly roll down into the deeper, true minimum. In this scenario, the cosmological constant and the acceleration we observe are the properties of our current false vacuum state. It's stable enough to have lasted for 14 billion years, allowing galaxies, stars, and life to form. But it may not be stable forever. At any random point in space-time, a quantum fluctuation could trigger a catastrophic event, the nucleation of a bubble of true vacuum. This bubble would be a sphere of space where the fundamental laws of physics are different, where the Higgs field has a different value, and where particles have entirely different masses and properties. The laws inside this bubble would be utterly alien to our own. The true terror of this event lies in its expansion. The walls of this bubble would expand outward at nearly the speed of light, driven by the enormous energy difference between the false vacuum outside and the true vacuum inside. As it expands, it would release a colossal amount of energy, and any structure, any planet, star, or galaxy caught in its path would be instantly and completely obliterated. There would be no warning, no chance of escape. The fundamental constants of nature would change in an instant, and all matter would be reconfigured according to new, unknown laws. It would be the ultimate end, not with a slow fade or a rip, but with a sudden, silent, and total rewrite of reality itself. The chilling part is that this isn't just speculative fiction. It's a rigorous prediction within the standard model of particle physics. The measured mass of the Higgs boson suggests that our vacuum may indeed be metastable, not absolutely stable. The calculations indicate that the universe is likely in a false vacuum state. The good news, if it can be called that, is that the predicted half-life for such an event is astronomically long, far exceeding the current age of the universe. The probability of it happening in any given region of space in any given year is vanishingly small, but it is not zero, and in an infinitely large universe or a multiverse, such an event becomes not just possible but inevitable somewhere at some time. This theory reframes the mystery of dark energy from a what to a why. If our vacuum is false, then the cosmological constant is simply the energy density of this temporary state. Its small, non-zero value is a measure of how deep our local valley is and how far we have to fall. The fact that it is so small might be a clue that we are perilously close to the edge of stability. The vacuum metastability event presents a cosmic future that is both certain and uncertain, a fate that could befall the universe at any random moment, ending everything in a blink, yet a fate so statistically remote that we have built a cosmos upon its fragile foundation. It suggests that the force accelerating the galaxies apart might be the very signature of our universe's latent instability, a countdown clock we cannot read, ticking toward an unknowable zero. What if the accelerating expansion of the universe isn't an objective feature of reality, but a phenomenon that only emerges because we are here to observe it? This 19th mystery plunges us into one of the deepest and most philosophical questions in all of science, a place where the quantum weirdness of the very small collides head-on with the cosmic scale of the very large. It asks whether the true nature of dark energy is forever beyond our grasp because the very act of measurement by conscious, localized observers like ourselves is what creates the appearance of acceleration in the first place. To grasp this radical idea, we need to revisit the most famous conundrum in quantum mechanics, the measurement problem. In the quantum world, particles don't have definite properties like position or momentum until they are measured. Before observation, they exist in a blurry cloud of probabilities, a superposition of all possible states. It is the act of measurement itself that seemingly forces the particle to choose a single, definite reality from this haze of possibilities. This is famously illustrated by Schrödinger's cat, a thought experiment where a cat in a box is simultaneously alive and dead until someone opens the box to look, at which point its fate is sealed. For a century, physicists have debated what this means. Does the conscious mind of the observer play a fundamental role in collapsing the wave function and defining reality? Or is there a more objective process at work that we simply don't yet understand? Now, scale this problem up to the entire cosmos. Cosmology has always assumed that the universe has an objective, observer-independent history. The Big Bang happened, inflation occurred, galaxies formed, all whether anyone was there to see it or not. But what if that's not the case? Some theoretical physicists are now proposing that certain large-scale properties of the universe, including its rate of expansion, might not be well defined until they are measured by localized observers within it. In this view, the cosmological constant, lambda, might not be a fixed number written into the fabric of space-time. Instead, it could be a quantum variable that remains in a fuzzy superposition of possible values until the cosmic history is measured by beings like us, living within a galaxy at a specific point in time. This leads to a startling possibility. The acceleration we measure might be a result of our own existence as observers constrained within a specific type of environment. We can only exist in a universe that has produced galaxies, stars, and planets. These structures can only form in regions where the initial density fluctuations were just right, and where the expansion history allowed for gravitational collapse. Our very presence as observers therefore selects for a particular cosmic history. When we go to measure the expansion rate, we might be inadvertently selecting the value of the cosmological constant that is consistent with our own existence, a cosmic version of the anthropic principle, but operating through the mechanism of quantum measurement. The acceleration isn't something dark energy is doing. It's something we are finding because it's the only outcome compatible with the fact that we are here to do the finding. This idea is deeply intertwined with the concept of quantum entanglement applied to the universe itself. In quantum mechanics, entangled particles share a connection that transcends space, instantly influencing each other's state. On a cosmological scale, the idea is that different parts of the universe, or even different possible histories of the universe, could be entangled. The value of the cosmological constant we measure here and now might be correlated with conditions in the distant past or in faraway regions we can never see, all part of one vast entangled quantum system. Our local measurement doesn't just reveal a pre-existing fact, it helps define a property of the whole. The implications of this are enough to make your head spin. It suggests that a complete theory of dark energy might be impossible without also having a complete theory of quantum measurement, a theory that explains how objective reality emerges from quantum possibilities. It blurs the line between the universe and the observer, implying that we are not passive witnesses to a cosmic drama unfolding on a stage independent of us. Instead, we are active participants, and our observations are inextricably linked to the very reality we are trying to measure. The mystery of dark energy thus becomes more than a puzzle about a missing component. It becomes a profound inquiry into the nature of reality itself, challenging us to consider whether the cosmos can ever be fully understood from within. This idea brings us to a theory of breathtaking scope and ambition, one that dares to apply the most radical principle from black hole physics to the entire cosmos. This is the 20th mystery, the holographic dark energy model, a proposal that suggests the energy density accelerating the universe isn't determined by the contents of space, but by its very boundaries, as if our three-dimensional reality is a holographic projection of information encoded on a distant two-dimensional surface. To grasp this, we need to journey back to a discovery about black holes that shocked the world of physics. In the 1970s, Jacob Bekenstein and Stephen Hawking found that a black hole's entropy, a measure of its information content, is not proportional to its volume as you might expect, but to the surface area of its event horizon. This was a profound clue. In everyday life, the entropy of a system, like the gas in a room, scales with its volume. But for a black hole, the maximum amount of information it can contain is limited by the area surrounding it. This led to the holographic principle, the mind-bending idea that all the information describing a volume of space can be thought of as encoded on a lower dimensional boundary enclosing that space, much like a three-dimensional image is encoded on a flat, two-dimensional holographic film. The holographic dark energy model asks a simple but revolutionary question. What if this principle doesn't just apply to black holes but to the entire universe? Our observable universe also has a boundary, a cosmological horizon set by the distance light has been able to travel in 14 billion years. This model proposes that the dark energy density we measure isn't an arbitrary constant. It is fundamentally determined by the size of this horizon. Specifically, it suggests that the energy density of the vacuum should be proportional to the inverse square of the infrared cutoff, which is typically taken to be the size of the future event horizon. In far simpler terms, the amount of dark energy in any given volume of space is capped by the amount of information that can possibly be stored on the surface area that contains it. This creates a stunning and elegant connection between the largest scales and the smallest. In quantum field theory, we have an ultraviolet cutoff, a high-energy limit beyond which our theories break down, often associated with the Planck scale. This UV cutoff prevents us from getting infinite answers when we calculate the vacuum energy, but it still gives us that impossibly huge number. The holographic model introduces a cosmic infrared cutoff, a largest possible scale, the horizon of the observable universe. The genius of the idea is that it links these two extremes. It proposes that the UV cutoff isn't arbitrary, it is dynamically determined by the IR cutoff. The physics of the very small is intimately tied to the physics of the very large. The maximum energy of particles is constrained by the ultimate size of the cosmos they inhabit, preventing the vacuum energy from reaching its predicted catastrophic values and instead leaving behind the tiny, residual energy we see as dark energy. This approach offers a tantalizing potential solution to the cosmological constant problem. Instead of a mysterious cancellation of 120 orders of magnitude, the holographic principle imposes a natural bound. The vacuum energy can't be infinitely large because the universe simply doesn't have enough information storage capacity on its boundary to encode such a reality. The energy density is automatically regulated to a small value that naturally evolves with the size of the cosmic horizon. As the universe expands, the horizon grows and the holographic dark energy density slowly decreases. This presents a clear, testable difference from a pure cosmological constant, which would remain unchanging. However, this beautifully simple idea faces its own set of challenges when confronted with observational data. The model makes specific predictions about how the equation of state parameter W should behave. For it to accurately describe our universe, the parameter often needs to be slightly less than -1, venturing into the territory of phantom energy, which brings with it the eventual prospect of a big rip. Current observational data, which strongly favors a value very close to -1, places tight constraints on this model. Furthermore, the choice of the infrared cutoff isn't set in stone. While the future event horizon is a natural candidate, other proposals like the Hubble horizon or the particle horizon have been explored, each leading to different expansion histories and challenges in matching the observed properties of the universe. Despite these hurdles, the holographic dark energy model remains a powerful and compelling framework. It is more than just another theory. It is a paradigm shift that forces us to think about cosmology in an entirely new way. It suggests that the key to understanding the universe's acceleration may not be found by staring into the void, but by studying its edges, by recognizing that the true laws of physics might be written not in the volume of space, but on its horizon, in a cosmic code we are only just beginning to decipher. Yet even the powerful simplicity of the holographic principle cannot fully quiet the persistent whispers of discord hidden within our most prized snapshot of the infant universe. This brings us to our 21st mystery, a deep dive into the statistical ghost stories imprinted on the cosmic microwave background. Beyond the striking axis of evil, the CMB holds a gallery of other, quieter anomalies, strange features and asymmetries that, while less dramatic, collectively challenge the pristine uniformity of our standard model and may be pointing toward a more complex history for dark energy itself. Perhaps the most famous of these is the so-called CMB cold spot. Located in the constellation Eridanus, this is a large, circular region of the sky that is significantly colder than the surrounding microwave background. In a universe that is supposed to be statistically isotropic, a feature this large and this cold is incredibly rare. the standard explanation that it's simply a random low point in the Gaussian fluctuations has a probability of about 1 in 200, unlikely enough to raise eyebrows. This has led to more exotic proposals. One captivating idea is that it could be the imprint of a cosmic texture, a flaw in the structure of spacetime itself, left over from a phase transition in the early universe. Another, even more mind-bending suggestion is that it could be evidence of a collision with another universe in the multiverse, a bruise on our cosmos from a primordial encounter. But there's another, more direct connection to our main story. Could the cold spot be a signature of dark energy? Some models of dynamical dark energy, particularly those involving cosmic supervoids, suggest that such an immense underdensity in the distribution of matter could gravitationally lens the CMB photons passing through it, leaving a cold imprint exactly like the one we observe. While this explanation is still debated, it demonstrates how these anomalies force us to consider that dark energy might not be perfectly smooth, but could have textures and variations that leave subtle marks on the oldest light we can see. Then there is the matter of hemispherical asymmetry. When cosmologists divide the CMB sky into two hemispheres, they find a puzzling difference. The fluctuations in one half of the sky appear to have a slightly higher average amplitude than the fluctuations in the other half. It's as if the universe was fundamentally slightly lumpier on one side than the other at the moment of recombination. The standard model of inflation predicts a universe that is uniform in all directions. It has no preferred axis and certainly no preferred hemisphere. This asymmetry, sometimes called a dipole modulation, is another feature that is very difficult to explain within our established paradigm. One compelling line of inquiry suggests this could be a sign of pre-inflationary physics. The idea is that the universe already had some primordial unevenness before inflation began, and that the hyper-fast expansion stretched these initial imperfections across the entire sky, freezing them into the CMB as a permanent, large-scale asymmetry. This would mean that inflation did not erase everything that came before it. It preserved a fossil of a more ancient, more chaotic era. For dark energy, the implication is profound. If the seeds of the universe's structure were not perfectly planted by inflation, then the evolution that led to the dominance of dark energy might also be more complex and less uniform than we assume. The force accelerating the universe could itself have subtle variations, its strength ever so slightly different in one direction than another, a concept known as anisotropic dark energy. The list of anomalies goes on. There is a curious lack of correlation in the CMB fluctuations at very large angular scales, meaning the hot and cold spots don't seem to be talking to each other across the widest expanses of the sky in the way our models predict. There are strange alignments between the plane of our solar system and certain features in the CMB that stubbornly refuse to go away no matter how carefully we subtract foreground emissions. Each one of these on its own could be dismissed as a statistical fluke, a trick of the light, or an unaccounted for systematic error in our magnificent but imperfect telescopes. But together they form a pattern of unease. It is the nagging feeling that the universe is trying to tell us something that our current theories are not equipped to hear. These anomalies are not necessarily evidence that the entire lambda CDM model is wrong, but they are strong hints that it might be incomplete. They are the faint cracks in an otherwise stunningly successful edifice, suggesting there is deeper physics to be discovered, perhaps tied to the very first instance of time. For dark energy, this could mean that its nature is intertwined with the conditions that existed before or during inflation. Perhaps the field that drove inflation is somehow related to the field that now drives acceleration. Maybe the value of the cosmological constant wasn't set randomly, but was influenced by the same primordial asymmetries we see frozen in the CMB. These statistical ghosts are more than just curiosities. They are the threads that, if pulled, could unravel our current understanding and weave a new, richer tapestry of the cosmos. one where the dark energy dominating our present is a direct legacy of the universe's turbulent and asymmetric birth. What if the two greatest mysteries in cosmology, dark matter and dark energy, aren't caused by unseen substances or strange energies at all, but are instead the cosmic equivalent of a mirage, an illusion created by our fundamental misunderstanding of gravity itself? This 22nd mystery takes us into one of the most radical and ambitious theories proposed in recent decades, Eric Verland's theory of emergent gravity. It suggests that gravity is not a fundamental force of nature, but rather an emergent phenomenon, a side effect of the way information is stored and processed on the boundary of the universe. In this view, the phenomena we attribute to dark matter and dark energy are simply gravity behaving in a new way on enormous scales, a behavior that emerges naturally from the deep quantum structure of spacetime. To grasp this monumental shift in thinking, we need to step away from the idea of gravity as a force that pulls objects together. Instead, Verland invites us to think about gravity in terms of entropy and information. Entropy is a measure of disorder, but in information theory, it also represents the amount of hidden information in a system. The second law of thermodynamics states that entropy always increases. The universe constantly moves toward a state of greater disorder. Now, here's the revolutionary leap. Verland proposes that gravity isn't the cause of this change, but its consequence. He argues that gravity is an entropic force, much like the pressure in a gas is an emergent property of countless random particle collisions, not a fundamental force itself. Gravity, in this picture, arises because systems naturally evolve toward states of higher entropy, and the rearrangement of matter is the universe's way of maximizing the disorder or information content associated with space itself. This is where the connection to dark matter emerges in a stunningly elegant way. In the standard picture, the rotation speeds of galaxies are far too fast to be held together by the gravity of their visible stars and gas alone. We invent dark matter to provide the extra gravitational glue, but Verland's theory offers a different solution. He calculates that the visible matter in a galaxy alters the entropy or the information content of the surrounding spacetime. This modification creates an additional gravitational effect, an extra pull that exactly mimics the presence of a halo of dark matter. In this scenario, there are no mysterious, invisible particles flying around. Instead, what we call dark matter is just the manifestation of ordinary matter interacting with the entropic underpinnings of spacetime. The theory makes a specific prediction. The apparent dark matter contribution should be tied to the distribution of normal matter in a very precise way. And for many galaxies, this prediction matches the observed rotation curves remarkably well without needing any free parameters. But emergent gravity doesn't stop there. It also aims to tackle dark energy. The model suggests that the accelerated expansion of the universe, which we blame on dark energy, is also a result of this entropic perspective. As the universe expands, the amount of information or entropy associated with the cosmic horizon increases. This growth in cosmic information drives a continuous process of spacetime emergence, which manifests as a constant negative pressure, a repulsive force that perfectly mimics a cosmological constant. In one grand, unified framework, Verland's theory attempts to sweep away two of cosmology's biggest unknowns by arguing they are not things to be discovered, but different faces of the same underlying principle, that gravity and spacetime themselves are not fundamental, but are born from the quantum information processing happening at the boundaries of our perception. For all its breathtaking elegance, emergent gravity faces immense challenges. The mathematics involved is formidably complex, pushing the boundaries of theoretical physics and drawing upon advanced concepts from string theory, thermodynamics, and information theory. This complexity makes it difficult for other physicists to fully evaluate and develop the idea. More critically, the theory must pass rigorous observational tests, and here it has encountered significant hurdles. While it successfully describes the rotation of many isolated galaxies, it struggles to explain the gravitational behavior of the largest structures in the universe, particularly galaxy clusters. Observations of colliding galaxy clusters, like the famous Bullet cluster, show a clear separation between the visible matter, which slows down due to gas friction, and the gravitational lensing effect, which maps the total mass. The standard dark matter model explains this beautifully. The collisionless dark matter particles pass right through the collision, so the mass is located away from the visible gas. Emergent gravity, which ties the extra gravity directly to the visible matter, has a much harder time accounting for this separation, as the gravitational effect should stay with the stars and gas. Proponents are working on more sophisticated versions of the theory to address this, but it remains a major point of contention. The true value of Verlaine's bold proposal may not be whether it is ultimately proven right in its current form, but in how it forcefully redirects the entire conversation. It challenges physicists to reconsider the very nature of gravity, space, and time, pushing them to explore connections between information theory and cosmology that were previously unexplored. It represents a paradigm shift as significant as the move from Newton's absolute space and time to Einstein's relativistic fabric. Even if emergent gravity itself is eventually superseded, its legacy will be the powerful idea that the answers to our deepest cosmic mysteries may not be found by looking for new particles in the dark, but by re-examining the nature of the stage upon which the cosmic drama unfolds, recognizing that space, time, and gravity themselves may be collective illusions emerging from a deeper, fundamental reality of quantum information. But what if the ultimate answer to the mystery of dark energy lies not in the vastness of space, but in the very nature of time itself, or rather, in its shocking absence from the fundamental laws of the universe? This 23rd mystery takes us to the heart of quantum cosmology and to perhaps the most profound equation you've never heard of, the Wheeler-DeWitt equation. Proposed in the 1960s by physicists John Wheeler and Bryce DeWitt, this formula was a monumental attempt to apply the rules of quantum mechanics to the entire cosmos to find the wave function of the universe. Yet in doing so, it produced a result so bizarre it has haunted theoretical physics ever since. The equation suggests that time, as we experience it, does not exist at a fundamental level. Let's break down why this is so strange. In standard quantum mechanics, the famous Schrödinger equation describes how a quantum system evolves over time. But the Wheeler-DeWitt equation, which is essentially the Schrödinger equation for the whole universe, is different. It lacks a time variable. The term that would represent the flow of time simply cancels out. The equation is static, timeless. It describes a universe that just is, a single, frozen quantum state encompassing all of reality from the Big Bang to the far future all at once. In this view, the flow of time is not a fundamental feature of the cosmos but an emergent illusion, a narrative our conscious minds construct from a deeper, unchanging reality. This is the problem of time, a deep philosophical chasm between our everyday experience and the cold mathematics of quantum gravity. This is where the connection to dark energy becomes absolutely fascinating. Some physicists have proposed that the cosmological constant, lambda, might not be a physical field or energy, but rather a direct consequence of this timeless nature of the universe. In the context of the Wheeler-DeWitt equation, solving for the wave function of the universe requires imposing a boundary condition, a rule that tells us what the universe was like at the beginning. One of the most famous proposals is the no-boundary proposal put forward by James Hartle and Stephen Hawking. It suggests that before the Planck time, the distinction between time and space blur, and the universe has no initial boundary, much like the North Pole on a globe has a defined location but no edge. When you work through the mathematics of this proposal, you can derive a probability amplitude for the universe to have a specific value of the cosmological constant. Intriguingly, the most probable value is not zero, but a very small positive number. In this scenario, dark energy isn't a substance or a force we need to add. It emerges naturally as a quantum gravitational effect, a necessary feature of a universe that popped into existence from nothing with a specific, self-consistent quantum state. The implications of this are enough to reshape our entire conception of reality. If the Wheeler-DeWitt equation is correct, then the accelerating expansion we measure is not something the universe is doing in time. It is an intrinsic, frozen-in feature of the universe's overall quantum structure. We are not watching a movie of the cosmos unfolding. We are, in a sense, traversing a single, timeless frame, and the sensation of time passing, along with the observation of galaxies receding, is how our limited classical perception interprets this grand, static quantum truth. This perspective offers a potential, elegant solution to the cosmological constant problem. The vacuum energy calculated by particle physicists might be a red herring, a number that belongs to a framework that mistakenly treats time as fundamental. The true value of lambda might be determined by the global topology and quantum boundary conditions of the entire universe, a number that is small not by miraculous cancellation, but by the requirement of cosmic self-consistency. Of course, this is perhaps the most radical and speculative frontier of cosmology. The Wheeler-DeWitt equation itself is fiendishly difficult to work with and interpret, and connecting its abstract solutions to the tangible, observational data we collect is a monumental challenge that remains largely unsolved. Yet it represents a breathtaking synthesis of ideas, weaving together the problem of time, the origin of the universe, and the nature of dark energy into a single, profound tapestry. It suggests that to finally understand the force pulling the cosmos apart, we may need to first let go of our most basic intuition, the relentless and universal tick of the clock, and embrace the possibility that we are all part of a single, timeless, and complete cosmic moment. What if the two dominant forces shaping our universe aren't operating in isolation, but are locked in a secret, cosmic dialogue? We've been treating dark matter and dark energy as separate entities, one clumping under gravity to build the cosmic web, the other acting as a smooth, repulsive force tearing that web apart. But this 24th mystery proposes a far more intimate and dynamic relationship, an interacting dark sector. Imagine these two invisible giants aren't just coexisting, but are actively communicating, transferring energy between themselves in a way that could elegantly unravel some of cosmology's most stubborn knots. The most compelling problem an interaction could solve is the profound coincidence we discussed earlier, the puzzling fact that we live in the brief cosmic era where the densities of matter and dark energy are comparable. If they are interacting, this timing is no longer a bizarre accident. It becomes a natural, stable equilibrium. Think of it like two connected reservoirs of water. One reservoir, dark matter, has been steadily draining as the universe expands, its density dropping. The other, dark energy, has remained constant, but if you connect them with a pipe, you can transfer water from one to the other, maintaining a balance between them for a much longer period. In cosmological terms, a continuous, tiny energy transfer from dark energy into dark matter, or vice versa, could keep their densities locked in a similar ratio across billions of years, making our current epoch of observation far less special and far more inevitable. This interaction acts as a cosmic feedback mechanism, naturally explaining why we find ourselves in this Goldilocks zone. This energy exchange wouldn't just alter the background expansion of the universe, it would leave dramatic fingerprints on the growth of the largest structures in the cosmos. Dark matter's great triumph is its ability to gravitationally collapse to form the halos that galaxies call home. But if dark energy is constantly feeding energy into the dark matter particles, it could effectively make them heavier or change how they move, potentially preventing them from clumping as efficiently in the early universe. Conversely, if dark matter is decaying into dark energy, it would slowly erode the very gravitational scaffolding from within. Both scenarios would suppress the formation of galaxy clusters and alter the entire tapestry of the cosmic web in ways that are, in principle, measurable. The precise statistics of how galaxies are clustered today and the rate at which that clustering has grown over time becomes a powerful test for these interaction models. Some versions of the theory can even help alleviate the persistent Hubble tension, as the altered expansion history might bring the early and late universe measurements into closer agreement. The challenge and the beauty of this idea lies in its testability. Unlike some more abstract concepts, an interacting dark sector makes specific, falsifiable predictions that upcoming telescopes are poised to investigate. The next generation of cosmological surveys, like those from the Vera C. Rubin Observatory and the Euclid Space Telescope, will map the distribution of galaxies and the effects of gravitational lensing with unprecedented precision. They will be able to detect the subtle imprint of this energy transfer on the large-scale structure of the universe. If dark matter and dark energy are indeed interacting, these instruments should find evidence of a universe where structure grew at a different rate than predicted by the standard non-interacting model. They might detect a signature that the strength of dark energy's influence has evolved over time in a way that can only be explained by a conversation with its invisible counterpart. We are on the verge of either discovering this hidden dialogue or ruling out a wide class of these compelling models, forcing us to accept that the two greatest mysteries of the cosmos, despite their intertwined dominance, might after all be strangers in the void. And so we arrive at the final, and perhaps most humbling, mystery of all, one that stretches our imagination from the practical limits of survival to the ultimate philosophical meaning of existence in a cosmos dominated by dark energy. We've explored what dark energy might be and where it came from, but this last question is perhaps the most human of all. Where is it taking us, and is there anything we or any other form of intelligence can possibly do about it? The answers force us to confront not just the fate of the universe, but the very purpose of consciousness within it. Let's begin with the stark, physical reality of our far future, a timeline so vast it defies human comprehension. If dark energy is indeed a true cosmological constant, the universe will continue on its current trajectory for eons beyond counting. In about 100 billion years, every single galaxy not already gravitationally bound to our own local group will have been pushed beyond our cosmological horizon. Their light will have redshifted into complete invisibility, and the night sky for any future astronomers in our galaxy will be utterly, profoundly black. An empty void punctuated only by the faint, dying embers of stars within our own island universe. All evidence of the Big Bang, of the expansive cosmic web, of the universe's rich history, will be permanently erased from view. The universe, from any local perspective, will appear static, empty, and lonely. This is the era of heat death, or the Big Freeze, where star formation ceases as interstellar gas is depleted or becomes too diffused to collapse, and one by one, the stars themselves will burn out, leaving behind a sparse graveyard of black holes, cold neutron stars, and dead planets, all drifting endlessly apart in an ever-cooling, expanding void. This is the bleakest possible outcome, a cosmos where life and information are not destroyed violently, but are instead isolated and rendered irrelevant on a scale so grand it negates any sense of cosmic purpose. But is this truly the end of the story? This is where we shift from passive observation to the most speculative and awe-inspiring realm of cosmological engineering. Could a sufficiently advanced civilization, armed with a complete understanding of physics, find a way to not just survive but to thrive in such an environment? The theoretical possibilities, while bordering on science fiction, are rooted in the known laws of physics and are a fascinating thought experiment in ultimate resilience. The first and most famous proposal is the concept of a Dyson sphere, a megastructure envisioned by Freeman Dyson that would encapsulate a star to harness its entire energy output. But in a dark energy-dominated era, a single star's energy is a fleeting spark. A truly advanced civilization would need to think far bigger. They might become what futurists call a type Roman III civilization on the Kardashev scale, one that can harness the energy of an entire galaxy. They could theoretically dismantle planets and stars to build a vast galactic-scale engine, a system of structures to collect every last joule of energy from the dying embers of their galaxy before the last stars wink out. Their survival would depend on mastering energy efficiency to a degree we can scarcely imagine, perhaps even learning to tap into the quantum fluctuations of the vacuum itself, extracting tiny amounts of energy from the seething foam of virtual particles that underlie spacetime. But even this is a temporary fix in a universe where usable energy is constantly being diluted. This leads to an even more staggering proposition. What if such a civilization could directly harness the source of the expansion itself? Could they build a dark energy engine? If dark energy's energy density remains constant as space expands, it represents a truly limitless energy source, but one that is incredibly diffuse. Tapping into it would be like trying to power a city with the gentle pressure of a breeze that blows through every cubic centimeter of space. The engineering challenges are incomprehensible, requiring technologies that manipulate the fabric of spacetime on a grand scale. Perhaps they could create localized regions where the cosmological constant is altered, or even devise a way to catalyze the decay of the false vacuum in a controlled manner, releasing a burst of usable energy without triggering a universe-ending catastrophe. These are ideas that push the boundaries of what we consider possible, but they illustrate a profound point. The ultimate fate of intelligence may not be predetermined by cosmology, but could hinge on its ability to master the cosmos itself. Yet, even if survival for billions of years is technically possible, it leads to an even deeper, more unsettling philosophical question: to what end? What is the meaning of existence in a universe that is increasingly cold, dark, and empty? If the cosmos inevitably trends toward a state of maximum entropy, a state of no information and no change, then does any action, any achievement, any thought ultimately matter? This is the existential threat posed by dark energy. It's not just a physical force, it's a narrative force that seems to write a story with a hopeless ending. The response to this, however, might be the most optimistic and beautiful idea in all of cosmology. It's the concept that the meaning of the universe isn't written in its final state, but is created by the conscious observers within it. The physicist Freeman Dyson himself argued that an open, expanding universe need not be hostile to life. He suggested that an infinitely creative mind could continue to process information and find meaning indefinitely, even in a cooling cosmos, by thinking slower and slower, conserving energy and stretching subjective time across the eons. In this view, the interior world of consciousness becomes the entire universe for that intelligence, a rich, boundless landscape of thought and experience that exists independent of the external darkness. Perhaps the final, greatest achievement of intelligence won't be to escape the universe, but to understand it so completely that it can generate its own purpose, creating a tapestry of meaning that is immune to the cold equations of entropy. The story of dark energy, then, is not a verdict of meaningless oblivion. It is the ultimate challenge, a cosmic dare to any species that looks up at the stars and wonders. It dares us to learn, to adapt, to engineer, and ultimately to find a reason to be, even when the last star has faded from the sky. The accelerating universe doesn't end the story of life, it simply begins its most difficult and profound chapter. And so we reach the end of our journey through the cosmic shadows, having explored 25 of the most profound mysteries that shroud dark energy in enigma. From the staggering numerical failure of the cosmological constant problem to the philosophical unease of the coincidence, From the terrifying phantom energy and the big rip to the dynamic elegance of Quintessence. We've ventured into the string theory landscape and its multiverse of possibilities, wrestled with the stubborn discord of the Hubble tension, and dared to imagine we might be living in a giant cosmic void. We've seen how the swampland conjectures challenge our very foundations, and how the fate of information itself hangs in the balance of an accelerating horizon. We've considered the alternative explanations, from the running vacuum and the early dark energy hypothesis to the lithium problem and the unified Chaplygin gas. We've connected it to the quest for quantum gravity, explored the holographic principle, and investigated the statistical ghosts in the CMB. We've even entertained the radical ideas of emergent gravity, the problem of time in the Wheeler-DeWitt equation, and the possibility of an interacting dark sector, all before contemplating the ultimate fate of intelligence in a cooling cosmos. Each one of these mysteries on its own represents a frontier of human ignorance so deep it could consume a career. Yet together they form a single monumental puzzle, the greatest in all of modern cosmology. Solving any one of them wouldn't just fill a blank space in our textbooks. It would shatter our current understanding of reality and force a scientific revolution. Cracking the cosmological constant problem might finally unite quantum mechanics and gravity, determining the true nature of dark energy, whether constant, dynamic, or an illusion, will define the ultimate fate of every particle in the universe. This isn't abstract science, it is the fundamental quest to understand the stage upon which all existence plays out. The most thrilling part is that we are not passive observers in this story. We are living through the golden age of cosmological discovery. Right now, the Vera C. Rubin Observatory is preparing to begin its legacy survey of space and time, a 10-year project that will map the cosmos with unprecedented depth and detail. The Euclid Space Telescope is already racing through the void, its keen eyes focused on measuring the subtle distortions of billions of galaxies to trace the invisible hand of dark energy. And on the horizon, the Nancy Grace Roman Space Telescope stands ready to discover thousands of distant supernovae, charting the expansion history of the universe with a precision we can only dream of today. These are not just machines, they are time machines designed to read the cosmic story written in the darkness. The data they will send back to Earth over the coming years and decades holds the potential to finally tilt the scales, to rule out entire classes of theories and provide the first solid clues toward a real answer. The mysteries of the dark energy era have persisted for a quarter of a century, but their resolution might be closer than we think. So stay curious. Look up at the night sky with a sense of wonder, knowing that the vast, empty blackness between the stars is not empty at all. It is filled with questions, and we are only just beginning to learn how to ask them. The greatest discoveries in the history of our universe are still ahead of us, waiting for the right combination of human ingenuity and cosmic light to finally bring